Bismillahirrahmanirrahim. Assalamualaikum and a very good afternoon. Okay, this week we are going to steps in the third chapter of the course entitled Fourier transform, in which you have the signal in time domain that will be converted into frequency domain omega. Okay, we have seen a time domain signal being converted into frequency domain in Fourier series. So today we're going to look at the difference between Fourier transform and Fourier series. Okay, the chapter can be divided into three main parts. The first one is the introduction into Fourier transform, followed by Fourier transform properties, and lastly the application of Fourier transform. Okay, some brief introduction on Fourier transform. Okay, if you revise back the Fourier series transform time domain signal of continuous time domain signal into frequency domain, in which the frequency domain signal you have in spectral lines, either it is in single-sided or double-sided. Okay, if you still remember, if you have continuous time signal, for example cosine function, so in frequency domain using Fourier series, you will be having single-sided spectrum or double-sided spectrum. But in Fourier transform, the signal in time domain is in non-periodic shape. Okay, meaning that the signal is not repeating itself by the same duration t, and the signal will be converted into frequency domain or omega domain, which leads to continuous spectral distribution at all frequencies, not just harmonics. Okay, in Fourier series, you can see that the signal, the spectrum covers each harmonic. For example, this is omega 1, omega 2, and so on. Okay, but in Fourier transform, it will transform a non-periodic signal in time domain. For example, you have this and this and somewhere there. Okay, this is for example non-periodic signal, and the spectrum you have will look something like this. Okay, it's continuous lines, covers all frequencies, so all frequency omega 1, omega 2, omega 3 up to infinity. Okay, because you can't even see every single harmonics as compared to the Fourier series. Okay, so Fourier transform is an application of Fourier series when the period of the signal is approaching infinity. Okay, why Fourier transform is needed? So this FT represents the Fourier transform. So it will be much easier to study or to manipulate the signal in time domain, in frequency domain, and many applications as listed, basically using Fourier transform in analyzing the system. Okay, let's look at the comparison between Fourier series and Fourier transform, and how the non-uniform signal in time domain is represented. Okay, for example, if you have this signal, okay, you can see that the basic signal, the fundamental signal repeating itself by the same t. Okay, same goes to this one. You can still see that this is the t and the same t is repeated, okay, in the next harmonic. Okay, same goes to this one, the third one, but you can see that the t now increase. Okay, even you can't even see the next harmonics. But how about the last one? This is when you can just see the basic shape. This is the basic shape, but you don't know how or when the signal is terminated, or how big the t is. So you don't know what is the t values. So when you don't know the fundamental derivation, so this is called non-periodic signal. So what happened in frequency domain? If you have the first until the third signal, you can still see the harmonics. So you can represent the spectrum by considering each harmonic. So you have the first harmonic, second harmonics, third harmonics, and so on. Okay, when the T gets bigger, okay, now the T increase, you can see that the F getting closer, the frequency getting closer if compared to the top two. Okay, now the F getting closer, okay, due to the increasing T. But what happens when you have the unseen T? You don't know how long the T is. So the signal, the spectrum, or the signal in frequency domain can be seen as a line spectrum. Okay, line spectrum up to infinity, because you don't know how small. Okay, how small the F is. Okay, for example, like this. So you can't even know which harmonics is which. Okay, due to the very high T, the very high value of T. Therefore, the F getting very, very, very small. So you cannot represent each single harmonics. Okay, so that's why when T approaching infinity, so the spectrum will appear as lines. Okay, let's look at another example. So look at the first one. Okay, this signal, you can see the T, the fundamental T naught. So it's repeating the same shape repeated with the same T. Okay, so when you can see the periodic signal with constant T, so you can estimate the spectrum by having each harmonics, the magnitude at each harmonics. But when you look at the second and the third signal, so the second one, so you only see the fundamental shape, the basic shape, but you don't know what is the T. Therefore, the spectrum will appear as lines. Okay, so this is the non-periodic signal. Okay, same goes to the third one. Okay, you can't even notice whereabout is the fundamental T. So still you don't know the fundamental T. Therefore, the spectrum will appear again as lines. So these two, the second and the third signal represents the Fourier transform signal in omega domain. Okay, so there are two steps or two methods to perform the Fourier transform from signal in time domain. So the first method is the Fourier integral, and the second method is by using the Fourier table, Fourier transform table, or Fourier transform pairs from the table. Okay, let's look at the first method. When you have a signal in time domain Vt, so to get the signal, the spectrum in frequency domain, or the Fourier transform of Vt, so you need to perform integration of the signal in time domain multiply with e minus j omega t dt. Then you get the Fourier transform of signal Vt. And then in order to get back the signal in time domain, when you have the signal in frequency domain, so you need to do inverse Fourier transform by again integrating the v omega, and then finally you will get Vt, the signal in time domain. So this is called Fourier transform integral, and this one is the Fourier transform or inverse Fourier transform. So this is the inverse Fourier transform. Okay, let's look at this example. So we're going to try two methods. The first one using Fourier integral, or the integration of the signal in time domain. So given your signal in time domain Vt equal to delta t, so by using the first integral or Fourier integral, you need to integrate this particular signal in order to get v omega. So now your Vt is equal to delta t. So perform the integration. So if you notice that signal delta t is this. Okay, when you have a signal, a pulse at t equal to 0. So the signal only appear at t equal to 0, meaning that the integration is performed only at t equal to 0, negative j omega t, when t is exactly at 0. Okay, so when you perform this integration, the outcome is, or the output is 1. So in this case, when you have a signal Vt equal to delta t, so your v omega equal to 1. So this is the impulse delta t in time domain. So the spectrum appear as lines with constant 1. Okay, let's look at how to solve this by using Fourier transform pairs. Okay, from the table. So again, we are going to use the same equation. So you will compare the first method, the Fourier integral, with the second method using transform pairs from the table. So the first step, you need to look at the functions in the table. Look at the closest function in time domain. Okay, you need to refer either in the first column. So isyarat meaning this signal. Okay, so bentuk gelombang is the waveform in time domain. Okay, so if you are given the waveform, so you can compare with the second column. If you are given the equation, so you need to compare with the first column. So in this case, you'll notice that the time domain signal is impulse function. So this is the impulse function. Next, you need to refer to the third column that represents the Fourier transform of the signal in t. So the Fourier transform is 1. Okay, jumaan Fourier meaning this is the Fourier transform. Okay, so the signal, when you have a signal Vt equal to delta t, so v omega equal to 1. So it's the same as the first method. Okay, but still you need to understand the fundamental integration in order to get the Fourier transform. Okay, let's look at another example on different shape of signal in time domain. So assuming that this t is approaching infinity. Okay, same goes to the left side, negative infinity. Okay, so what happened when you have a rectangular signal in time domain when the t approaching infinity? So how the Fourier transform or the spectrum looks like. Okay, if you look at this signal, so if you have the t, smaller t, if you have t a bit smaller, so you can plot the spectrum by using Fourier series because you know the t. So this, in this case, it is in periodic signal if the signal is close, or you can identify the t. But if the signal now appear like this, a rectangular signal v naught, and t over 4 and minus t over 4. So you don't know the t. Therefore, you cannot represent the spectrum as lines as Fourier series. So it needs to be represented in lines. Okay, so the dashed line represents the Fourier transform of the rectangular signal when the t approaching infinity. Okay, let's look at the same shape of signal, rectangular signal. So how to get the Fourier transform of this rectangular signal when t is not known. So when t assuming approaching infinity. Okay, so by using the first method, Fourier integral, so you need to perform the integration. In this case, the Vt is the rectangular function with magnitude A. So this is your Vt. So perform the integration. So from minus t0 to t0. So after integration, you'll get this V omega. So this is the Fourier transform of the rectangular signal. However, in Fourier transform, usually the rectangular signal will be transformed into sinc function. Okay, SINC, sinc function. So sinc A, for example, equal to sine A divided by A. So in this case, to convert sin into sinc function, so you need to divide the sin omega t naught divided by omega t naught. So in this case, you have the 2a omega. So then you have sin omega t naught. So to get this into sinc function, it must be divided by whatever in the bracket, so omega t naught. So when you introduce additional function, so you need to multiply here with omega t naught. Okay, so you can simplify the equation. So the Fourier transform of rectangular signal is equal to 2a t naught divided by, so this equation is already in sinc omega t naught. Okay, so you introduce this, so you need to multiply with the same function. So this represents the sinc function. So the coefficients or the magnitude is 2a t naught as you simplify the omega. So the signal of rectangular function, a non-periodic rectangular function. So in Fourier transform or in frequency domain, the signal appears as lines in sinc shape. Okay, this is the sinc shape when the signal attenuates towards 0. You have maximum at 0, so the signal something like this, and it slowly attenuates. So this is sinc function. Okay, so now let's try the second method using Fourier transform pairs from the table. So first you need to compare with the closest shape of function in time domain. So in this case, you have rectangular function. Obviously, this is the closest shape. Okay, so next you need to look at the Fourier transform equation of the given signal. So in this case, by comparing the given signal and the signal in the table, so you need to properly define the variables involved. For example, the magnitude here is A and same goes to here, so the magnitude is A. But if you look at the duration, so here is t0 and minus t0, but here is tau over 2 and minus tau over 2. So if you look at the size, the size is basically tau from the table, but the size of the given signal in this case is 2 T0. So you need to properly modify your Fourier transform to fit in the information you have from the given signal or the given function. So in this case, from the table, okay, from the general equation, given is when you have a rectangular t over tau, so this tau is the size of the or the width of the rectangular. So in Fourier transform, the v omega, don't forget Fourier transform, you need to use capital letter. V omega equal to the equation you can see from the table, from the third column. So now you need to compare with the given signal. In this case, your Vt equal to a rectangular t is the domain, and tau is the width of the signal. So in this case, the width of your signal is 2 T0. So the width of your signal is 2 T0, meaning that in this case, tau equal to 2 T0. Or from the function, you can see that your T0 is equal to tau over 2. So tau is equal to T0. So now look at the equation in Fourier transform. So a tau. So now you know that your tau equal to 2 T0. So replace tau with 2 T0. Sinc function omega tau over 2. So omega tau over 2 is equal to T0. So now you can simplify your equation. Okay, so in this case, when you have a rectangular t over 2 T0, so the Fourier transform equal to this equation. Okay, this is how the magnitude and phase spectrum of rectangular signal in time domain. So you have the signal just now rectangular in time domain. So this is how the signal looks like. So this is your Vt. So your V omega is supposedly the sinc function. So this is how the sinc function looks like. Okay, but in this case, if you notice, this is the magnitude. So all negative amplitude will be positive. So the magnitude spectrum can be drawn as this. And this is the phase spectrum. So since that's negative, amplitude becomes positive, therefore that's phase shift. So negative to positive, that's shift by pi. So that's why you will see either it is positive pi or negative pi. So if you derive back the sin function into exponential function, you will see that's double-sided spectrum with alternate phase shift. Okay, let's have another example. Given the signal Vt equal to Ae minus Atut. Okay, look at the complete equation for a larger than 0. So find the Fourier transform of Vt. So if using the first method, so you need to perform the integration. Okay, so this is your Vt. Don't forget the basic equation is the integration of Vt e minus j omega t dt. So this is your Vt. So perform the integration when a larger than 0 up to infinity. So you get v omega equal to a divided by a plus j omega. So now let's look at the second method. Okay, from Fourier transform table, look at the closest equation. So sometimes you may see from the table that's ae minus at only. Sometimes the equation may appear ae minus, for example like this. Okay, so you need to compare the closest equation. So in this case, the function aeat multiply with ut. So this is the actual equation. So from here, from the third column, you'll notice the Fourier transform of the same signal. So this method 1 and method 2 produce the same answer. Okay, so to get the magnitude and phase spectrum, so you need to convert this rectangular function into polar form. Okay, lastly, when you have a signal, a spectrum, so how to get back your VT? So you need to perform inverse Fourier transform. Again, two methods available. The first one is integration, and the second one by using the Fourier transform pairs or table. Okay, so to use the first method, you need to perform integration of the signal. So now you have the V omega, right? So you'll get the VT. Perform the integration and you'll get VT. Or you can use the Fourier transform pairs or table. So the first step, you need to look at the, okay, in time domain, you look at here first, the signal in time domain first. But in Fourier transform, to convert the omega domain into t domain, so you need to look at the third column first, look at the closest equation, and then reverse back to the left hand side, so you'll get the inverse Fourier transform the signal in time domain. Okay, with that I end my session, my presentation for the first topic. So see you in next topic.